Greetings to you. We will continue our discussion on potentiometry. In the last class, I had taught you about electrodes of the first kind, second kind, third kind and hydrogen electrode, how we can use different kinds of electrode for different applications. And because the standard hydrogen electrode is difficult to set up and handle every time, we go for reference electrodes and whose values have been determined very accurately, which can be used for day to day purposes. So, according to the Nernst equation, potential of a reversible electrode permits calculation of the activity or concentration of the component of a solution. So, using Nernst equation, if I have an electrode dipped in a solution, I can find out its concentration, that is the analytical technique. So, I write Nernst equation something like this: EAG is equal to E naught AG plus RT by NF ln AG plus divided by AG, that is log of oxidant divided by reductant, and then it is connected to another electrode, that is not hydrogen electrode, but a calomel electrode. ESCE is calomel electrode, that is standard calomel electrode. So, standard calomel electrode, that is electrode of mercury with in equilibrium with its sparingly soluble salt. Okay. So, here I have two beakers, okay, and one contains silver nitrate solution with a silver electrode, and then I have a salt bridge here. The salt bridge will contain nitrate solution, potassium nitrate or something, that will permit the passage of NO nitrate ions through this, and silver ions will be moving towards cathode here, and nitrate ions will be moving towards anode here. So, what is the other electrode, anode? That is calomel electrode. So, a calomel electrode is constructed using a very simple system, that is I have a tube here, and you see this small area in this here. It is mercury here at the bottom, and above mercury I have a small quantity of mercurous chloride, that is Hg2Cl2, and above that I have a saturated potassium chloride solution. Okay. This is saturated, filled with saturated chloride solution, and that is dipped here. So, the electrons can be in contact. Here I have an external connection. So, this is plus, this is minus. So, if I have a system something like this, this is agar. Agar is nothing but something like gelatin, that is how salt bridges are made. So, I can write half cell equation reaction for EAG is equal to E naught AG plus RT by NF ln AG plus by AG, and ESCE I do not have to write the equation, but I know the value from the books. So, I can write E cell is given by EAG minus ESCE. What is EAG? EAG is E naught plus RT by NF ln AG plus and minus ESCE, this I am writing here. So, E naught AG log of AG ln log of AG, I can transfer it on the left side, is nothing but that is equal to E cell minus E naught AG. I am retaining this side, transferring everything on the left hand side. So, E cell minus E naught AG, this comes here, plus ESCE, this minus sign becomes plus, ESCE goes there, and then divided by 2.303 RT by NF. This 2.303 appears because I am converting that into log scale, not natural logs. So, this value you should remember for all the time to come if you want to be an electrochemist. 2.303 RT by NF is 0.0591. Okay. So, if it is n is equal to 2, then it will be different. Put n is equal to 2 and find out whatever comes out like that. And so, I put the value E cell is measured on the potentiometer, that is plus 400, and E naught Ag is minus 0.799, that I get it from the table, standard table, and ESCE is 0.246 volts, that I get it from the table, from the textbooks available. E 0.0591 is the value of 2.303 RT by NF, and so what I get is 2.59. So, if I know log Ag plus is equal to 2.59, I can find out what is Ag plus. Anti-log of this would be nothing but Ag plus would be 2.57 into 10 raised to minus 3 molar. So, what does it mean? If I have a solution of silver nitrate, okay, I just connect it like this, with ammonium nitrate as another solution. I do not have to do any experiment, just connect it, put a calomel electrode, connect wires plus and minus, calomel is to negative, silver to positive, and note down the potential voltage. How much I am getting? 2.59. Take the anti-log of this. So, that tells me the concentration of silver plus is 2.57 into 10 raised to minus 3. I do not have to do any experiment at all. Just by noting down the potential, I can find out what is the concentration. That is the beauty of potentiometry. Okay. So, here you have to note down a few points. For example, we always subtract more negative from the more positive. So, which is more negative? More negative is 0.799, isn't it? 0.4 is positive, 0.246 is positive, more negative is 0.799. So, that we are subtracting from the more positive, and 2.303 RT by NF, this I have already told you that it is 0.0591 at 25 degrees. If you want very accurate values, use the T value temperature of the solution as Kelvin. Okay. Then PAg, PAg is nothing but minus log of Ag plus. It is just like pH, negative log of hydrogen ion. Here it is negative log of Ag plus ions. Okay. So, consider one more example now. I am taking a platinum electrode, dipping in 0.1 normal ferrous sulphate with standard calomel electrode as a counter electrode. Okay. A potential difference, I just connect with a saturated calomel electrode or whatever it is, a potential difference is 0.395 is what I note down on my voltmeter. So, I should know what is the concentration of ferrous and ferric, and how much ferrous has been converted into ferric by oxidation. I think you are all very familiar with ferrous ferric oxidation systems. Whenever you cut an apple, within no time you see a brown color on the cut side of the apple. That is oxidation of ferrous to ferric. Anywhere in the world, wherever there is ferrous solution, there is always it always reacts with air to get oxidized to ferric. So, even if you take ferrous sulphate as the as a medicine, ferrous fumarate is a B12 medicine, tablet, and you want to know how much of ferrous is there after some time. You want to know how good is the medicine, you have to find out how much of the ferrous is there. So, if you want to find out what is ferrous ferric concentration in a given solution, what I am going to do is I will say do not do any experiment, connect the solution to a platinum electrode, put another calomel electrode, measure the voltage. I will tell you what is the concentration of the ferrous and ferric. How I am going to do that is very simple. I simply write E ferrous ferric to ferrous. This is the redox system. EMF of the ferric to ferrous solution is dependent upon the sum of E naught Fe3 plus by Fe2 plus. This is the standard reduction potential of ferrous, plus RT by NF ln ferric to ferrous. Okay. This is oxidized state and reduced state, and whenever oxidized state reduced state both are in solution, the higher valency would be in the oxidized state. So, it is very simple to write, you do not have to know a lot of chemistry to write it. Okay. So, then measure the EMF. What is the E cell? EMF is nothing but E cell, potential of the cell when you set up ferric ferrous solution with platinum electrode and calomel electrode. So, I write ferric ferrous EMF plus RT by, here it should be E naught. Okay, I have forgotten there to write there, plus RT by NF ln Fe3 plus by Fe2 plus. So, now I want to know what is log of Fe3 plus by Fe2 plus, and I keep this on the left hand side and transfer all other information, this information on the right hand side. So, RT by NF is nothing but the difference. So, log of Fe3 by Fe, this E cell minus E naught Fe3 by Fe2 Fe2 plus ESCE, because I am connecting the E cell. Remember, here also we had done a similar exercise, ESCE, when I transfer it becomes plus. Okay. So, same thing happens here. So, E cell is equal to log of Fe3 by Fe2 is equal to E cell minus this thing, put the values, and what I got is 2.20 volts. Okay. 2.20 volts when I get, I can simply take the anti-log of this value 2.20 and tell you that 6.3 into 10 raised to minus 3 is the value or what I get, that is approximately 0.63 into 10 raised to minus 2, that is 0.63%. So, without determining any doing any chemical analysis, I am going to find out what is the concentration of ferric and ferrous. If you just give me a solution of ferric and ferrous in which you want to determine your ferric ferrous solution. So, that is the beauty of potentiometry. You appreciate that? Good. So, now we will talk about concentration cell. What is a concentration cell? Very important concept. Imagine I have two electrodes placed in solutions in the same kind of solution, but differing in concentration. I take two beakers, there are two solutions of different concentration, but same material. Okay. So, but they are connected with the salt bridge also. So, the potential between the two electrodes must be related to the concentrations, because it is the same electrolyte in both the beakers. So, I can write something like this. silver chloride electrode, okay, silver electrode in contact. This line represents a contact, single contact. Silver is in contact, direct contact with silver chloride solution, silver chloride precipitate, here it is, and no, here it is liquid solution, and that is in contact with silver chloride ions in the solution of concentration x, and then I have a salt bridge in another, dipping in the other beaker, in which the other part of the salt bridge is there. I have a chloride solution in contact with silver chloride and Ag plus. This concentration I know, S. So, two cases arise. What are the two cases? Case 1, suppose the standard is 0.1 molar. Its a single electrode potential is given by ES is equal to 0.222, that is silver chloride, as measured E naught, as measured against standard hydrogen electrode, that is standard reduction potential, minus 0.0591 log of oxidant divided by reductant. Okay. So, 0.0591 log of 1 log of 0.1. So, this gives me 0.281 volts. You can calculate this and find out for yourself what is the voltage. So, if this concentration I already know. So, I know how much is the voltage I am going to get. Then I take the unknown concentration, which you want to find out how much of silver is there. We need to find out lot of silver analysis. We need to analyze, especially photographers and other people who develop the photographs in actual print. They dip it in silver bromide solution and sodium sulphite, etc., and silver gets consumed while printing. So, the concentration of silver goes down and they keep on changing, and they want to know how much of silver is there in the solution. So, I have a solution which I do not know. I want to find out how much of silver is there. So, if the unknown is more concentrated, say 0.1500, then I can write Ex is equal to 0.222. This is common because it is E naught of silver's Ag plus by Ag minus 0.0591 log of 0.1500. Now, I am assuming that it is 0.1500 concentration. Then what I should get? This value is 0.271. So, E cell is, I have same electrode, both of them cancel out. So, the only difference of potential should come from the solution. So, E cell is nothing but the difference of the two half cells. So, what is the first half cell? 0.281, second half cell is giving me 0.271 because the concentrations are different. So, E cell is Es minus Ex, that is 0.010 volt. Okay. So far so good, no problem. Now, consider another situation. Okay. So, look at the slide now. Suppose an unknown is having 0.680 molar silver solution, unknown X. The other one is 0.1 volts. Okay. So, I write an expression 0.222 minus 0.0591 log of 0.0680, that gives me 0.291 volt, and E cell is nothing but the difference between the two, just like in the last slide, and I am getting 0.010 volts, and how much I am getting in the previous slide? It is 0.010 volt. So, when the concentration is 0.15, I get 0.01 volt, and when the concentration is 0.680, also I get 0.1 volt, 0.01 volt. So, any measured potential is open to ambiguous interpretations. That we can avoid this by noting that the interpretation corresponds to the more positive of the two. So, the concentration cell, I should note down which is the polarity. So, if the polarity is positive, I say yes, this solution is 0.680, the other one is, if it is negative, then the concentration could be 0.1500. So, any measured concentration, the same voltage if you get, there could be two alternatives of the unknown composition, one of the two. So, if you switch, you should get the correct one. Okay. So, the concentration cell, I have given you an example of silver chloride now. Now, I can give you concentration cell of hydrogen ion itself. Just look at it. I have an inner calomel electrode. I have a hydrogen ion solution of pH 7 as buffer. I have a glass membrane that is like a salt bridge, and then I have a solution whose pH I want to know, and then I am connecting to external SC. So, this is essentially like what we had talked about concentration cell now. Yes, this is AgCl, Cl minus in contact with Cl, AgCl, Ag. So, same thing I am writing here. Inner electrode, saturated calomel electrode, pH 7 buffer, one membrane and one test solution, and this concentration I know pH 7 buffer, another is external. So, I can define a pH system like this. So, by similar analogy, I should be able to find out what is the concentration of hydrogen ions in the test solution. That is how we make our pH meters. Okay. So, we go back. How do we define a pH? So, pH is nothing but negative logarithm of the activity of the hydrogen ion concentration expressed in molarity. This definition you must by heart, but this is not correct, because we should say it is this is the correct definition, thermodynamically correct definition of pH, but in practical terms we say pH is the negative logarithm of the concentration of hydrogen ions expressed in molarity. Replace that term, this activity, with concentration, that is practical. Okay. So, pH is, we write like this, pH is negative log of AH plus, A is activity, that is also equal to negative log of H plus ion log to the base 10, and for a solution of 2.0 into 10 raised to minus 4 molar HCl, if I have a solution of 2.0 into 10 raised to minus 4 molar hydrochloric acid solution, what would be the pH? Very simple, apply this equation, write pH is equal to negative log of, instead of AH plus, write 2 into 10 to the power of minus 4 like this, and then solve this equation. This is minus 4 will become 4, minus log 2, okay, negative is there. So, log 2. So, that will give me 3.699 and that is pH is 3.70. So, if I know the concentration of any acid, strong acid, okay, it will not work for dilute weak acids. So, pH is nothing but negative log of hydrogen ion concentration that is available. A strong acid we know the concentration, and if I prepare well and good, so I can find out what is the pH of the solution if I know the concentrations. Okay. Now, the measurement of pH is accomplished with hydrogen electrode in a cell, concentration cell. I have already explained to you calomel electrode, then H plus buffer versus in contact with glass membrane, in contact with a unknown solution, in contact with calomel electrode. So, such a concentration cell, the potential is given by this expression 0.0591 log of H plus standard divided by H plus unknown. Standard solution we know concentration. So, for a saturated calomel electrode, its potential is 0, log 0 is 1. So, E cell is nothing but 0.0591 log of H plus, that is 0.0591 pH. I am replacing minus log of H plus by pH. Okay. So, pH is nothing but E cell divided by 0.0591. So, for calomel electrode it is minus 0.246 if I use a calomel electrode instead of a standard electrode. So, calomel electrode shows minus 0.246 volts with respect to standard hydrogen electrode. So, if I have a cell of unknown solution of unknown hydrogen ion concentration connected to a calomel, then my pH I should be able to define E cell would be, actual E cell would be E cell minus 0.246 divided by 0.0591, I have to subtract. So, that will give me the pH. Commercial electrode pH meter can be conveniently made by using a calomel electrode. Okay. So, all the pH electrodes, pH meter what you see around you are built on this principle. You take a solution of hydrogen chloride or any acid connected to a saturated calomel electrode, measure the E cell, subtract calomel contribution, divide it by 0.0591 and the range is 1 to 14. They put a dial. So, the current generated would be used to move the needle across the dial from 0 to 14. So, all these things were there until 1950s and 60s. Most of the pH meters that were available in the market were based on this principle, the analog. Nowadays, we have digital pH meters as well as the more sophisticated ones, and there are improvements in the electrodes also, and that is known as glass electrode. So, what is a glass electrode? So, the glass electrode is a new invention. Of course, it is there since since 1960s or 70s, say 60s approximately. And nowadays, there are hundreds and thousands of beautiful glass electrodes in the market, and the same version, but the same principle. So, thin membranes of certain varieties of glasses are permeable to hydrogen ions across the glass membrane. That means, if you take a solution, an acid solution, put it in a special glass membrane, it will allow the passage of hydrogen ions on both sides. So, essentially what I am doing is I am creating a concentration cell with one solution inside the glass membrane, another solution outside the glass membrane, which will permit movement of hydrogen ions and across. So, a thin membrane of certain varieties of glasses are permeable to hydrogen ions, and a glass electrode is reversible. It contains a solution of known and unchanging pH, that is a chloride containing buffer. It should be known pH and it should not change over a period of time. So, that is how a glass electrode is made, and a reference electrode. Again, reference electrode I can make a calomel electrode or a silver chloride electrode. So, the tube is permanently sealed at the top, because I do not want a known concentration buffer to spill out and lose its concentration or evaporate. So, a glass electrode, what I am going to do, silver chloride electrode and glass membrane and a platinum solution, external mercury solution. So, the tube is permanently sealed at the top. When this is dipped into an unknown, a concentration cell results like this. This I have already shown you, and inner calomel pH 7, glass membrane, test solution. External SE, I can put silver chloride electrode here and silver chloride electrode here and measure the pH. So, for such a cell, the pH is given by E cell. What is E cell now? It is glass. So, I write Eg minus E cell divided by 0.0591. So, Eg is a constant that includes the potential of reference electrodes and additional small spurious potentials called as asymmetry potential that arises out of unequal strains in the glass, and the glass electrode is special for each manufacturer. So, the glass electrode you have to standardize every time, and whenever you buy a glass electrode, that needs to be standardized with respect to standard solutions of pH 7, pH 4, pH 9 like that buffers, and then you should use it, because this Eg term what we had referred earlier, the asymmetry potential will not be the same for all types of glass membranes. Okay. So, the glass electrode is a routine analytical tool in any laboratory. In highly alkaline solutions, it gives certain error, because sodium ions, alkaline solutions, sodium ions will also move a little bit this side that side, and there will be an error of plus or minus 1 pH unit, but it can also absorb some specific ions, some erroneous results, but in general from 1 to 9, 1 to 12 pH you will not have any problem. Nowadays glass electrodes or pH meters with glass electrodes are available. They are known as combined electrode, combined glass electrode, a single cell containing both the electrodes, one reference and one standard, and they are available in the market with digital output and storage, and nowadays with microprocessor you can do a lot of things. So, therefore, it is essential to use buffers for standardization, and every time when you use a buffer you have to wash it number of times to make it memory independent. It should not remember the previous measurement. Okay. So, that is about the glass electrode. What we will do is we will continue our discussion about other types of electrodes for some time, and then we will look up some of the potentiometric titrations etc. in our next class. So, thank you very much. Have a nice day.